in this lecture we are going to talk about Verilog HDL implementation of voltage based constant on time control, and we will also show some experimental results. So, first we will talk about top down, we will revisit our top down design methodology, which we have discussed in the previous lecture. Then we will design constant on time modulator with minimum of time, and then we will show step by step Verilog HDL implementation of constant on time digital control. So, first we will recollect this block we have already discussed in the previous lecture. Then and we have discussed the basic constant on time concept in lecture 20 in our earlier NPTEL course. Now, we want to implement using Verilog HDL this block, and we want to synthesize and we want to prototype using FPGA. So, in this block it will accept the data from ADC, and it will also send ADC clock, and this Q transient is optional, we are not using. External clock is the clock which is high frequency clock 100 megahertz, high side and gate side low side gate signals we are generating from this, and the Q load which is for load transient, but here we are not making load transient because we want to operate in discontinuous conduction mode here. So, this is a block that we are going to now inside this block we need to consider this modulator. This is the heart of constant on time, where you need to have a constant on time modulator. So, this block is inside this block. Now, so if we talk purely the constant on time modulator with minimum of time, we have discussed what is there inside the box. We have discussed that this particular block in the previous lecture we have discussed, this is for constant on time, and this block will represent minimum of time. And more precisely, if we consider that overall constant on time modulator, I would say COT modulator, if this is your enable clock and this is your overall Q. So, we are dividing this part to be Q 1, this part to be Q 2. So, what we want that for Q 1, so whenever our enable pulse come, that means this is our enable pulse come, what we want is that first we want to show how does my Q 1 look like, how does my Q 2 look like, and finally, how does my okay. So, I will use a different place here, maybe I will erase. So, okay. So, let me draw here. So, let me draw here, let us say this block, and we can actually divide this into two pieces, this block, this block. Now, first we will have an enable clock. So, enable, so it is coming high here. Okay. Now, we want to write here to be Q 1, here it is Q 2 and this is Q out. So, we want to draw Q 1, we want to draw Q 2 and we want to draw Q out. So, in this case first whenever this pulse come, this will go high, and how long it will be enabled? It will be during this T on time. Then whenever the T on finish is counting, then this is the time Q 2 will be high, and this duration is what? This duration is T minimum time, the minimum of time. And what will be our Q out? The Q out will be goes high, low and low. So, I am just saying this point to this point it will release, that means suppose if we have another enable signal coming in, so this will only respond after this time. That means, during this time this will not respond. So, if another enable comes, this will not respond until the minimum of time is elapsed. So, it will only respond after this. That means, this Q can go high only here, that means it will enable. So, we need to make sure this enable signals should be placed here rather than here. So, it should not enable. So, that means, we need to generate this enable signal through a proper clocking. So, we will be using a clock manager. Q1 will be generated for the counter. So, it is customizable, you can set the timer, minimum time is also customizable. That is why, if you look at this, the particular block we are talking about. So, if you go back to our previous thing, these things, the synthesis, we want to synthesize this modulator, where we can vary, because if you go for adaptive on time, so the on time can be varied by simply varying this number. Similarly, we can vary the minimum on time. So, these things are possible by adaptation of this. Okay. We already discussed about the main module, clock generator, clock modulator and clock manager. So, the clock manager job is to generate the enable signal, that is very crucial, okay, and that also require H circuit. So, first we will go for constant on time modulator. So, this is the basic block. So, this is the overall control. So, we are talking about this control logic, and this is the main module. What is considered here? We are talking about this clock. We need a clock for the ADC, which is sitting here. The clock ADC is here. Then PWM high, it is coming from here. Then we have this PWM low, which is here, okay, and ADC data, which is coming from here. ADC data is coming, it is here. So, these are the input output port, and we have defined here. We are not using Q load, we actually set it to 0. So, that means in fact, we are not sending anything. We are not sending anything from here. So, that means, if you do not send anything, it will be set at a 0 position. And we know about the defining, how to define this quantity, that means input, output, vector input, and we are taking sign data, it is Q1.9 format, we have discussed earlier. Now, we want to parameterize, that means n timer, n min and n rep. N rep we have discussed earlier, this corresponds to V0 nominal to be 1 volt, that is the nominal voltage. This we have discussed earlier. Now, if you take the n timer, if you take this binary number, n timer here is nothing but, in decimal it will be 200. So, that means 200 time we are actually creating on time, because we have discussed that it will take 200 such cycle, 0 to 199 it will go, right, like this. And the minimum time we are taking 26 cycle, that means it will go up to 26. So, that we will have a 26, that means T minimum will be how much? 26 into 10 nanosecond, sorry 26 into 10, that is nanosecond, which is nothing but 260 nanosecond. And what is 10 constant on time? It is 200 into 10 nanosecond, which is 2 microsecond. But you can reduce it, because 2 microsecond may be large. So, these quantities are adjustable. Now, we are instantiating the clock generator circuit, which is taking the clock, high frequency clock, generating ADC clock, and we are generating an external clock. Why? I will tell you. So, this external clock, let us say if our let us say we are talking about the voltage. So, we are talking about this Q trigger, QTR. Suppose you start the circuit when the output voltage was 0. So, this guy was 0, and then this n rep circuit was actually, it was its own value. Now, since you are starting the circuit, so voltage, that means first this QTR will be high at the beginning of the circuit when you start, then your timer will be, Q will be high, for this on time, and we know there is a minimum off time that goes high. Now, this QTR actually high, because from the very beginning, as long as the output voltage is below the reference voltage, it will remain high unless it goes above. Since it is high, so even after this on time is elapsed and the minimum off time is also elapsed, there is no edge trigger signal. So, that means this enable signal, it requires a edge trigger to turn on this monoshot timer. So, that means if there is no edge trigger signal, it cannot turn on the timer and the voltage will collapse. So, we need to create this thing, that is why we are giving an external signal, which will actually I will discuss in the subsequent slide how this enable signal should be generated using external clock. That means, external clock, there is a fixed frequency clock which will check whether your the Q trigger is high. If it is high, there is no edge, then this will also generate an edge. That is like that. That is something. Similarly, suppose we want to synchronize your constant on time modulator with an external clock, then this external clock can be used, and we are not going to discuss the synchronization effect, but it is possible. But for the time being, let us say there is a clock. Now, we have a COT modulator where input is the enable signal. It has a high frequency clock which will generate the timer, on time and off time. It will take the data as an on time command, minimum of time command. It will generate the output Q out, and that Q out will be the output, and it will generate the Q finish. When, how does the Q finish is generated? Whenever the on time is elapsed and minimum off time is gone, this is my T of T mean, then this will generate a flag signal. That means, this will generate a flag signal, and which we are talking about Q finish. So, Q finish is not simply after finishing on time, it is after finishing on time followed by the minimum time, then it will say that you can now turn on the timer. That means, the on monoshot timer is relaxed or it is basically released. So, you can now turn on again, but until this minimum of time is not complete, it will not enable any further change. Similarly, during this process, if multiple enable signal come, it will not respond, because it will remain, it is a monoshot timer, it goes to the one state, then comes back after the on time, then minimum of time, then only it will entertain any further enable signal. So, that is why we need to generate a clock manager, so that which actually can manage this enable signal. So, the clock generator, I think we have discussed that this block was the same block we have used, which we have used for voltage mode and current mode. So, we are using we are using a this we want to generate a switching frequency clock, which is it will count up to 499, okay, and this will go up to NSW 0 to 499. For ADC, we are using just 3 clock, that means, we want to generate F ADC, which is F clock divided by 4, that is it. That means, it is 25 megahertz. So, this we have discussed earlier. Next, the COT modulator. This block we have presented, and this block also we have presented. So, how does it work? So, COT modulator, first the COT modulator is a sub module, or it is a module which is instantiated within the main module. It require an enable signal, this is the boundary of this. It require a timer signal, it require a minimum value, Q out is the actual out, Q finish is the finish. So, that means, you can imagine that this enable, this Q out, actually this modulator will show like, it will appear like this block, and yeah. So, it will take the data clock from outside, that is the clock. It will also need the timer command, minimum on time command, all these commands are given. Now, input is enable signal, then F clock, that is the high frequency clock here, this clock, N timer we have discussed, and output is the Q out and Q finish. Okay. Now, how are you going generating? So, N count and N minimum count, that means, we need 2 counter, one is this. So, this counter is here, another is this counter is here, and both we are taking 10 bit counter. it is unsigned counter, and we have defined RST, which is this signal here, and RST1, which is this signal here. These two are the register, and that will actually generate the whenever the change of comparators take place. And there are some Q temp, you can see this is the signal. So, let me use a different color, this is the signal, and this Q temp is this signal. Okay. So, here we want to erase this. Okay. Now, next, always at the end. So, this first we are implementing which logic? We are implementing this logic. So, this logic is here. Always at the pauses of enable or the pauses of this reset, then it goes inside. If check, if the reset is high, the Q temp is set to 0, because this is a RS flip flop. Otherwise, it will be 1, because this command will be executed only when either the enable high positive edge come or the positive edge the reset comes. And if positive edge reset come, that means if it is high, it will be 0, and if the enable reset come, if the reset is low, it will be. So, it is a reset dominated RS flip flop. Next, we want to implement this counter. So, this counter, it will check at every clock edge. First, it will check whether this output is high or low, because we want to implement this logic. So, it will take the Q output NOT gate, you can see NOT gate. If the Q output NOT gate is high, that means Q output NOT gate is low, that means it goes low, then this will be high, and in that case the counter is simply 0. That means, we are not going to count when this goes low. When this goes high, then this signal will be low and this reset will be released. In that case, the counter will start counting. Now, the counter will start counting and reset is 0. When reset will be high? When the counter will try to exceed the timer, and this is the comment. When the counter goes above or equal to the timer, then counter will be reset, and it will generate the reset to be high, that is the active high of the reset signal. So, this whole logic is to use this block. I mean, I would say this whole block is implemented by this Verilog code. Next, again we are implementing this block. This block is here. So, it takes the pauses of. Now, for the next stage, the reset RST of these pauses is like a enable signal, and RST1 of this will be the pauses, is like a reset signal. So, again if this signal goes high, then this output will be 0, and if this is not high and this edge come positively, it will be set to high. Next, again the same, we want to implement this logic. We want to implement this logic, which is this particular logic, and this is nothing but this. So, it is same as this block, where this counter will be 1 or 0. So, this is what, but now up to this point, I will say this is up to this point, this always block, where again it ends in the clock edge. If the temp out is 0, then it is disabled, counter will not be counting, reset is also 0, but if it is 1, then this will be reset is disabled, then the counter will start counting, okay? And this counter name is the minimum time, and the reset is 0. Once this counter exceed the minimum value, then the counter will be reset and the reset 1 will be activated. This will be, and this will actually implement this logic. Now, last, what is Q out? Q out assign where variable, it is the Q out, this signal you can check, ANDed with not of this. So, ANDed, this is the AND in the data flow modeling, AND operation, and this is the invert of this logic, which is nothing but this. And what is Q finish? It is the reset one, because this will allow any further action in the monoshot timer, because you have completed your on timer followed by minimum off time. That means, this is your T on, and here let us say you have completed your T min, then counter is allowed for further, you can trigger it further if you want, but till this point you cannot do anything. So, next is important part, how do you generate this enable signal? So, this is where it is coming. So, the enable signal generation, it require a clock signal, high frequency clock, QTR, which is the comparator output, because we have taken the voltage comparator. That means, as if you can assume this is the output voltage and the reference voltage in a very simple sense. Whenever output voltage goes above the reference voltage, or basically reference voltage is above, that means, if the output voltage falls below the reference voltage, this will generate a trigger pulse, and this we call it as a Q trigger. So, this may not be trigger as long as output voltage is below reference, all the time QTR is high. So, this is a QTR. Q external, I told that we will check the status after periodically. So, this is my external signal, which is a fixed frequency signal. So, it has a dual purpose. In this case, we are using to check the status, but in future you can use this clock to synchronize your time period of the monoshot timer, but we are not going to discuss that part. And F mean, that means, what is F mean? It will check whenever this minimum of time is elapsed, it will generate another trigger pulse. That means, it will generate a trigger pulse when this is we call it as F mean. What is the purpose? It will check whenever the off time is elapsed, it will check whether this QTR, that means output of the comparator, is still high. If it is high and if there is no edge, then this guy will actually create an edge, so that monoshot timer will be again activated. So, that means, monoshot timer will be only activated subsequently only after the minimum off time. So, that is why this F mean is generated. F mean, it will be enabled when your on time is elapsed followed by minimum off time is elapsed, then this will be generated, and we will check the status if the QTR is high. That means, what I am saying, if the QTR is high for long time, so the first time this is your QTR, for example. So, first time your, I think the monoshot timer will be enabled, that will disable for minimum of time. Now, this is your, I am saying the Q out. So, this is your T on, but after that T on, now your F mean will generate F mean. It will check, since it is high, it will create a pulse again. That means, you turn on the timer again, because you need to turn on, the voltage is already below. But suppose if the counter this is not turned on, then this signal will check at this stage. So, at this stage again this signal will come, and since QTR is high, it will again generate an enable signal. So, this is an enable signal, it is enabled here, it will further enable. But here, as if again counter goes high, it goes for this minimum and all. But during this time, if multiple enable signal comes, it does not matter once it is enabled, because it will not respond to the any external enable as long as this it is already operational. So, that is why it does not matter. So, this frequency clock is kept to make sure the voltage should not collapse, that means, we should turn on the enable timer. So, that is why you see I have generated the Q mean, which is a combination of QTR n. So, that means, I have ANDed this F mean ANDed with QTR, and QTR is also ANDed with F external. So, this I am calling as a Q mean, and this I am calling as a Q external, and now I am using an edge detection circuit. So, you can see that there is an edge detection circuit, and these edges are finally OR to get, and since these two edge only take this, we also need to consider another edge. What is that edge? The edge of the QTR itself. So, one is the QTR edge itself, because we also need to identify the edge of this guy as well. So, that means, this there will be an edge detection circuit if any edges come. So, one edge is a Q mean edge, sorry, this I will say F mean edge F external edge, another I want to say F QTR edge. So, all 3 edges will be detected and these 3 edges will be, this will be coming, this will be coming, these are all OR. So, finally, OR of all these phases, and that is my final enable signal. That means, enable signal edge is a OR combination of the edge of the QTR, the edge of the F mean and edge of the external, but all this edge will make sense in the timer only when you are allowed within this duration. If there are multiple edge come, it will not respond. So, this complete the implementation of. Now, if you go to edge detection, what does it do? Suppose if you take any signal, we want to detect edge, let us say this is my Q1 signal. What will do? I will delete this signal, this is my Q1 dash. Then what I will do? I want to take the positive edge. So, let us say this signal goes high here, this signal goes high here. So, naturally your this signal will go high low here. So, if you use an edge detection circuit, this will be your Q1. So, Q1 dash and this is Q1. So, Q1 and Q1 dash, if you pass through an XOR gate, then if this is your Q, let us say 2. So, the Q2 will be high during this time, Q2 XOR gate, but we want to detect. So, depending upon how much is the delay you are giving, that width will depend. Now, we want to detect positive edge. So, that is why after this you have to end with Q1, because this time the Q1 is high. So, it will detect, and this is my actually positive edge, I will say Q F1 edge. So, edge of this Q1 signal can be detected by this logic, and this is exactly what we did. Next, we have this modulator. Now, we want to generate this particular implementation logic. So, we will take, because we want to go close to analog comparator, but since we have a limitation in the clock, we are using ADC clock. So, we will check each ADC clock data is updating whether the ADC data is smaller than n rep. If it is smaller, that means output voltage is smaller than the reference voltage, then the status of the comparator goes low, high, that means this QTR will be high. This is my telling. So, this QTR is nothing but my comparator status. If it is above, then it will be 0. So, now since we are using only the not synchronous buck, the conventional buck, this output of the gate will simply go to the high side gate, this will be high side gate, and this will be low side gate will be set to 0. And what is Q out? Now, after all this discussion, you have to go to the module instantiation block, where instantiated the module. Yes. So, the Q out is the actual output of this counter monoshot timer, which is a combination of on time plus minimum of time. And then what is that is Q out? What is the enable? It is the output of the clock manager. I told you that you have to OR 3 edges. One is the edge of the QTR, another is the edge of the F min, another is the edge of the F external. So, all this combination, this will go to the enable time. So, this will complete the implementation of this block that we have discussed. Okay. Now, we want to show the hardware details. So, we are using the same converter that we have discussed, 200 microfarad cap, 1.8 microhenry inductor, 3.3 input voltage, 1 volt output. The switching frequency is varying, because it is a constant on time control, and we are operating in DCM, discontinuous conduction mode, because we are replacing, QL is set to 0. So, the body diode will come, okay, and load resistance we are setting 13.5. Now, with this we want to actually go for, so we are using ADC. So, it is the 10 bit resolution, we are using 10 bit ADC, and we are using a controller clock of 100 megahertz, but what is the ADC clock? We are using 25 megahertz. Okay, now this is the experimental result, where you can see this channel is the output voltage. So, his output voltage is 1 volt, is a reference voltage. This is my V0. You see, when the output voltage falls below reference voltage, then this on time is triggered, and one of the on time is elapsed. We will have a minimum of time, but that is not coming here. Then the voltage goes above and the voltage remain above, again it comes below, then again on time is triggered. So, this is your time period, which is the effective time period, and it is called pulse frequency modulation, because constant on time is a pulse frequency where the frequency varies with the operating condition PFM. So, it is a COT PFM, constant on time, because there are many PFM technique. One is the constant on time PFM, you can have a hysteresis PFM. So, there are different burst mode control is a different thing, but here. So, this is one of the waveform. The next waveform I want to show, this is the operation, but you see this time period they are supposed to be same, and these time periods are slightly. So, if you take T effective 1, T effective 2, so T effective 2 seems to be smaller than T effective 1. So, it is slightly vary. Why? Because we are not taking analog comparator, so that we do not have infinite resolution of the time. The time has a finite resolution, because it is taken, the data is taken after every 40 nanosecond, and during this 40 nanosecond your output voltage, actual output voltage might have crossed, but we are not taking action because the data is not available. As a result, this time quantization, you are actually getting some jitter in the time period in the T effective, which will be avoided if you simply use an analog comparator. Another thing, because of this time quantization, it may so happen when the on time is low, or basically input voltage is low, even if you apply a on time and your voltage is supposed to rise, but there will be always some spike in the output voltage, or there will be some the output voltage may, because it has gone down significantly down, one on time may not be enough to immediately take it up. So, then it is undergoing 2 consecutive on pulses. That is why it is like double, but we also discussed we are putting a minimum of time. So, we need to zoom this part and see whether it is happening or not. Yes, you can see there is a small portion of the time that we call T minimum. During this time the switch is turned off. So, that whatever algorithm we have discussed, it is actually working, but this problem is coming due to the time quantization. But what can be done, if you increase the input voltage for the fixed on time, your current will increase, because on time is fixed, input voltage increasing, the slope will increase, and you may not find this consecutive on time, but otherwise this will increase the ripple, because of the continuous on time the ripple may increase. But all this problem may be resolved if you use an analog comparator. Now, we are going to show the live demonstration of voltage based constant on time control, which is typically used for light load discontinuous conduction mode, where we are trying to improve the efficiency. So, it is also known as pulse frequency modulation, because where we have discussed that the switching frequency will linearly vary with the with the load current. So, in this we have already run the code, we have synthesized, and then we have generated the program file, and we have loaded the FPGA file dump into the FPGA. I am not going to show this step, because this is already we have done, and we have shown this step in multiple lectures. Now, we want to start, that means first the supply. So, we want to start with, let us say 3.3 volt, where it is sort of nominal voltage that we want to design, nominal voltage. So, this is 3.3 volt. So, if you see the scope, first of all you will find two things here. If we do a single shot, so there is, in some cases we are getting pulses which 2 consecutive on pulses, because this depends on the logic, because what is the logic here? When the output voltage goes below Vref, then we trigger a monoshot timer and then it gives a minimum on time, fixed on time, and we have discussed this in this lecture, what is the duration of on time. But now since the input voltage is 3.3 volt, actually if you zoom this portion, maybe we can continue. So if we take this position here, I just want to show the zoom version. So I want to show the zoom version of this. What is happening here? You can see there are two consecutive on pulses, and in between there is a minimum off time, because that we have discussed. That means if we take this waveform, so first there is a on time, and what is the on time? It is a 2 microsecond, on time is 1 microsecond. So one time 1 microsecond, but after this on time, it seems that output voltage was not even above the reference voltage, so it again hit the lower limit, and we have discussed we are not taking an analog comparator, we are taking an ADC which is running at 25 megahertz clock. So naturally there is a time quantization effect, that means sampling effect, that means we are capturing the sample which shows that it is below reference, that is why it is triggering another on pulses, and in between we have given a minimum of time which is I think 0.1, 100 nanosecond or maybe 200 nanosecond. But I mean if you zoom this further, we may figure out that what is the minimum duration. So the minimum duration seems to be around 260 nanosecond, that is the minimum duration. Okay, but nevertheless first time your switch turns on. Now since there are two consecutive on pulses, as a result it has injected a large number of energy, a huge energy. As a result you will find, if you run again, there is a sufficient gap between next pulses. Okay, so as a result you will find this. But if we do not select this, suppose if you select this, then you will find the regular operation where it should show PFM, that means it should show a fixed frequency and it should repeat. But we have discussed that since there is a sampling time which is 40 nanoseconds, so time resolution, the voltage, there is a mismatch between because your effective time period is not the integral multiple of 40 nanoseconds. As a result, there is always some quantization effect and there is a jitter effect, and that is actually coming here. But this large spike which is coming, that actually is still there. Now if we increase this input voltage, that means instead of 3.3 volt, we are increasing. You see, when the on pulse is sufficiently large, the occurrence of such high pulses are now going down. I mean these pulses are not coming, and you are getting more or less PFM operation. But what is happening? The peak current has increased because your on time is fixed and input voltage is increasing. As a result, the slope of the current is increasing, and as a result the current ripple is increasing. So it may increase the voltage ripple also. So that is one of the problem in constant on time if you use a timer based on time. And when you move to, I will demonstrate in another lecture, adaptive on time, where this can be taken care. But at this in this lecture I am going to show that you are getting a pulse frequency operation under light load condition. So in summary, we have discussed the top down design methodology of voltage based constant on time control. We have discussed design of constant on time modulator with minimum of time, and we have discussed step by step Verilog HDL programming constant on time digital control, and we have also shown some experimental case study. So in the subsequent lecture, we want to consider experimental case study with DCM, under DCM with constant on time, with PSM, pulse keeping modulation, as well as PWM. So these things will be compared in the subsequent lecture. That is it for today. Thank you very much.